Multivariable Calculus, Section 13.9, Change of Variables. T is a transformation from the UV plane to the XY plane. So here we have a nice rectangular region in the UV plane, and T is a function or transformation that will change that region and everything else on the UV plane into something curvy on the XY plane. But what we really want to do is go from something complicated to something simple. So T inverse is a transformation from the XY plane to the UV plane. And so what we're going to try to do is take a complicated problem and change it into a simpler problem. So here's another picture of T. XY is called the image of UV under the transformation T. If every point in the region of the UV plane that is the domain of T has a unique image in the XY plane, then T is called one-to-one. We like one-to-one, they're easier to handle. So here's our messy, curvy problem in the XY plane. The U curves are the XY plane images of horizontal lines in the UV plane. So we're going from lines to curves. And the V curves are the XY plane images of the vertical lines in the UV plane. So the vertical lines become curvy and the horizontal lines become curvy, and they're not necessarily oriented the way you see here. I mean, it depends on how you construct your transformation T. So here's another example. Let's say we have a region S in the UV plane, and we're using horizontal and vertical lines, and we take T and transform that whole region over into the XY plane. We get a different shaped region, and the lines become curves. So there's a U curve, although we could do it the other way, and that could be a V curve, but we could do a completely different orientation, rotate it 90 degrees and switch which ones are V and which ones are U. Now, of course, the point here is that we would probably want a nice region in the UV plane, not a messy one as shown in this example. And T inverse would take us from the complicated XY problem, change the variables into U and V to make the problem easier. So XI, is, under the transformation, is a function, X is a function of U and V, and Y is a second function of U and V in order to give us our new coordinates. And so the transformation here in 2 space is made up of 2 functions. And both those functions put together are our transformation T. There's our U curve. Now if that's our U curve, then this arrow, that blue arrow, represents the velocity vector along the U curve. And this velocity vector along the U curve is designated T sub U, and it's the partial derivative of x with respect to u times I plus the partial derivative of y with respect to u times j, and then there's the shorthand notation, xu comma yu in the chevrons. Likewise, along the v curve, we have a velocity vector, and the velocity vector along the v curve is designated T sub v, and it's the partial derivative of x with respect to v times I plus the partial derivative of y with respect to v times j, or for short in the chevrons, xv comma yv. Now, why are we looking at these velocity vectors? Well, we're going to need these to help us with our transformation. Okay, so now what you have here, the pink area is a curved area in the xy plane bounded by v and u curves, and the blue parallelogram is determined by the velocity vectors along the u and v curves. So what we can do is approximate the curvy regions in the xy plane with parallelograms determined by the velocity vectors along the u and v curves. Now, as the changes in u and v shrink to 0, then the parallelograms become closer and closer in area to the curved surface, and we can get the exact area using an integral. Now, the area of any one parallelogram is the length of the cross product of the two vectors determining the parallelogram, which we can evaluate in this 3×3 determinant. And the quick way to evaluate a 3×3 determinant is to first copy the first two rows, and then we multiply along the diagonals. But notice that most of the diagonals are going to yield 0. And so the only two that don't yield 0 are those. And so what we get for the cross product is xu yv minus xv yu times only k, because in the two-dimensional picture, of course, the k components were 0, and so the cross product is perpendicular to the xy plane along the k unit vector. Now we want the length of this cross product, and so since it's only got one term, we'll square it and then take the square root. So basically we're just going to have the absolute value of that coefficient. And so the length of the cross product is the absolute value of xu yv minus xv yu. And that's also known as the determinant. 2×2 determinant will also give you that same value, and as long as you make sure it comes out positive. And it's also called the partial derivative of x and y with respect to u and v. This is sort of a shorthand notation that your book uses. It may not be universal. Now what's going on here is that we're taking two vectors in two space and mapping them on for at each individual point, mapping that onto a real number, because we're going to get a number when we evaluate these partial derivatives at a particular point. And this has a special name. Definition: the Jacobian. The Jacobian of the continuous differentiable transformation t, which maps the uv plane onto the xy plane, is the real valued function that maps the uv plane onto real numbers, and it's defined by the determinant that we looked at in the previous slide. So our integral, if we have a double integral, a function in x and y, then in order to change it to the other plane, the uv plane, we need to perform our transformation, but then we need to integrate over the change of variables, which involves the Jacobian, and then the change in u and v instead of x and y. So this is our formula for transforming from one set of variables to a second set of variables. Notice that the region is different too, so your limits of integration change. Just like when you did u substitution last year, you had to change limits of integration as well as do all the change of variables. So let's look at change of variables in triple integrals. It's just an extension of the same idea. Our Jacobian now is a transformation from UVW space to XYZ space. And so instead of a 2×2 determinant, we just have a 3×3 determinant using the partial derivatives. And that's also known in shorthand as the partial derivative of x, y, z with respect to u, v, w. And so our integral, our triple integral, again, we change from xyz to the transformation of u, v, w, and then we integrate that over the Jacobian times the changes in u, v, and w. So now we're going to do some problems. Given u and v in terms of x and y, solve for x and y in terms of u and v, and then compute the Jacobian. So this is just a little exercise to get you used to all the notation and the computations. It can be tricky. Part A can be tricky. You have to use your algebra prowess. In this case, we've got linear equations, so we can use linear combinations. So what I first did was I took the first equation and multiplied the second equation by 2, and then when I add them together, then that gets rid of y, and I can solve for x in terms of u and v. And then something similar, I want to get rid of x this time, so I multiplied the first equation by -3 and added that to the second equation, eliminating x, and so now I can solve for y. So there's part A. And I think in this section I found doing this step in each of the problems actually the most challenging as the functions got more complicated. Part B, the Jacobian, there's the shorthand, is going to be the determinant using the partial derivatives, and in this case the partial derivatives are all constants, because for example if you look at the x value in part A, x is u plus 2v over 7, so the partial derivative of x with respect to u is just 1/7, the coefficient of u, and so on. And then you do your multiplication, 1/7 times 1/7, and then minus the other diagonal, which would be negative 6/49, and so you get 7/49, which is 1/7. Number 6. Given u equals 2x over x squared plus y squared and v equals negative y over x squared plus y squared, solve for x and y in terms of u and v and compute the Jacobian. Alright, now this is a little bit tricky, part A. What we're going to do is we're going to square u and v and add them together, and when we do that we get a nice simplification and we can solve for x squared plus y squared in terms of u squared and v squared. So then when we substitute that into our first equation there, we get an expression in terms of u, v, and x, because we get rid of the y that way and we can solve for x. And then we do the same similar thing to solve for y. We substitute in the second equation the 4 over u squared plus v squared. And I didn't show the work there, but that's what y ends up being. Phew. So you have to, use your great intellect to figure out what to do here. They're all these problems are doable, but they might be tricky. Okay, part B. The Jacobian, again, is the determinant of partial derivatives, and this time, we have quite a production. We have to use the quotient rule. So here comes the derivative of x with respect to u using the quotient rule. And now the derivative of x with respect to v using the quotient rule. The derivative of y with respect to u using the quotient rule. And then finally the derivative of y with respect to v, partial derivative. I should be saying partial derivatives with respect to v. And notice that in the first column, in both of those you treat v as a constant, and in the second column, for both of those calculations, you treat u as a constant. Well, this is a little messy, but it's just algebra. But I'm out of space, so let's move to another slide. Here's what we had. That simplifies quite nicely. And simplify, simplify, simplify. And so then what we want to do is multiply diagonally, and then multiply the other diagonal, subtract, and since the second one's negative, when we subtract we get a positive. And then when I multiply out the numerators and add them together, I get something that factors. Isn't that nice? And so the whole thing reduces to 4 over the quantity u squared plus v squared squared. And that's our Jacobian. And at any particular point uv, we would get a real number value for our Jacobian. Number 8. Substitute u equal xy and v equal x divided by y to find the area of a region bounded by y equal x, y equal 2x, xy equal 1, and xy equal 2. Okay, so I just took the picture of the region from your book, and notice that it is neither vertically or horizontally simple, and so our old methods really wouldn't work. And here's our formula. We want to make this transformation, and we want to make a nice transformation, and luckily the book gave us a suggestion, because coming up with the proper transformation is rather tough. Now, because we're doing area, our function is 1, so that simplifies it a little bit. All we need to do is get the Jacobian. So we're going to use these two expressions to first solve for x and y in terms of u and v. And notice that if we multiply u times v, the y drops out. Isn't that brilliant? Very smart of the authors to think of that. And so now we have x in terms of u and v. And if we flip v over and multiply, then we get rid of x, and we can solve for y in terms of u and v. That's actually the hardest part of these problems, in my humble opinion. So now we need the Jacobian, which involves the determinant of the partial derivatives. And you're getting really good at those, so I'm not going to belabor how to figure those out. But remember, in the first column, you treat v as a constant, and in the second column, you treat u as a constant. And then you multiply diagonally, and it comes out rather nicely. So now that we have the Jacobian, and we know our function is 1 because we're doing area, we can go ahead and set up our integral. But we have to know our limits of integration. So here's one of the points. And if we look at that intersection, I didn't show the algebra, but you just set the black curve and the blue line equal and solve, you get 1, 1 for that point. And so if we put those into our formulas up at the top, what are we going to get? And then across from that, if you go straight up, you get 1, 2 when you do the intersection of that black curve and the blue point. And so that gives you an x and y. So again, what we're going to do is we're going to plug those in, and we have to decide, are we going to do u or v? And I decided to let that be u. As long as you're consistent, it'll work out in the long run. So u is going to move from 1 times 1, which is 1, to 1 times 2, which is 2. Now, if we go the other way, that was a little bit harder to solve, but there's the x and y coordinate of that point and the x and the y coordinate of that point. And so v is going to be x divided by y. And again, I didn't show the calculation, but if you look up at the top, x divided by y is what v is going to be. And so for the root 2, it's obviously 1. And for the root 1/2, root 2, that's root 1/2 divided by root 2, which comes out to a half when you simplify it. So here's our integral, and you can decide whether to integrate with respect to u or v first. I decided to use u because then I just treat 1 over 2v as a constant, and then I'm going to evaluate that integral for u moving from 1 to 2. And so when I simplify that, I just get 1 over 2v because 2 minus 1 is 1. And then that involves log, so you get 1/2 the log of v evaluated from 1/2 to 1. And then that can be simplified to log of root 2. So the area of this little blue region is natural log of root 2. Number 10. Find the area of the region bounded by y equal x squared, y equal 2x squared, x equal y squared, and x equal 4y squared. And again, the book has given us a hint on how to do that transformation, which would be difficult to do on our own. Thank you, Mr. Textbook. And so to solve for x and y in terms of u and v, which is our first step, we're first going to substitute ux squared for y squared. And that gets rid of y and allows us to solve for x in terms of u and v. And then we're going to substitute vy squared for x, and that will allow us to solve for y in terms of u and v. So now here's our Jacobian. And again, in the first column, take the derivative of x in the first row and take the derivative of y in the second row. But in the first column, treat v as a constant, and in the second column, treat u as a constant. And then when we multiply diagonally, again, because this is a textbook problem, it simplifies fairly nicely, and that's our Jacobian. Now here's a picture of our region that I took from the book. And again, we've got to figure out our limits of integration. So what I did was I solved for u and v in these two equations so that I could, once I get the points on the xy plane, I'll have a formula to transform to u and v values. And so that intersection point, and again, I'm not showing the algebra, but I'm sure you're more than capable of setting those two equations equal to each other and solving. And then sort of up from there, we have another intersection point. And so again, this time I decided to make those u numbers. And so I plugged into that formula and got u going from 1 to 2. Now you can go up or down, sideways, it doesn't matter which direction you go in, because as long as you make sure you come out positive in the end. Then we have another intersection point and the last intersection point, and I plugged those into the v formula to get the limits for v. And I decided to go down from a 1, 1 down to the other point in order to come out positive. So v is going to go from 1 to 4. So our area is our double integral with the Jacobian, and again, because we're doing area, the function part in our formula is just a 1, so we can omit that. And this is a fairly easy thing to integrate. I decided to integrate with respect to v first. You could do it the other way around, it really doesn't matter. And I was out of room, so there it is again. So integrate with respect to v and evaluate that from 1 to 4. And then that just gives us, so I'm doing details here because you're doing v to the negative 1 from 1 to 4, so that's going to be 1/4 minus 1. That gets rid of the negative sign. And we have 1/3 times 3/4, so that becomes 1/4. And then that's an easy integral. Evaluated from 1 to 2. So we get negative 1/4 times 1/2 minus 1, which is 1/8. And that then is the area of that little region that we showed on the previous slide. And that's a lot of work. So now I leave you with a picture of a typical high school class, supposedly. Can you see any of your friends in this picture? I see Jack in the front row. Do you see him? So enjoy these problems, the last section of 3rd quarter, and I will be back with another lesson next quarter.